In this video, we want to discuss volume of revolution, which is one of the applications of integration in integral calculus. Now, what is this concept all about? The concept of volume of revolution is about finding the total volume of objects when it is being revolved around either x-axis or y-axis. When an object is projected through the graph, it could be what? It could be revolved around x or y. So in integration, we want to find the total volume of such object when it's being revolved around x-axis or y-axis. Then we talk about volume of revolution. While trying to find the total volume of revolution of an object, we use different methods depending on the questions given. So, I remain Dr. OJ. In this video, I want to discuss the concept of volume of revolution and as well show us the real life application of this concept. To start with, let us look at this example. Let's look at this example. Example of volume of revolution. The first example here, let's call this example 1. Find the volume. Find the volume of the solid. Generated by revolving the region bounded by y is equal to 2x minus x squared and y is equals to x. So we want to find the volume of the solid generated by revolving the region bounded by y is equals to 2x minus x squared and y is equals to x about the y-axis. So now this looks like, you know, for example, in a Cartesian plane, x, y axis, this x plus y plus. Now, we want this solid object to be revolved around the y-axis according to what we're given here. So that implies that probably, you know, let's take, for example, we are taking the positive side of it. So we have something like this. Let's say this is the object, this is the first graph, this is the second one. Let's assume that. And now we have this. So this object is revolving around the y-axis. If it was the other way around, then that means it's revolving around the x-axis. But according to this question, the object revolves around the y-axis. So now, what we are given here, we actually need limit of integration. We are given two curves here, these curves. So we need to get the limit of integration that will assist us to know the total volume of the object being revolved. So what do we do? Let's equate this curve with this, okay? Because this one is saying y is equal to this, the other one is saying y is equal to this. So equating them, we have what? Y is equal to 2x minus x squared. The other one is what? Y is equal to x. So by equating the two of them together, we have what? 2x minus x squared is equal to x. So now you collect like terms. You have what? 2x minus x squared is equal to 0. So, and 2x minus x is what? That's x minus x squared is equal to 0. So with this now, you can have what? Can factor out. So now say that x is common. So you have 1 minus x is equal to 0. So what does this mean? This one means what? X is equal to 0 or 1 minus x is equal to 0. Okay? That's our elementary algebra. Okay. So here, 1 minus x equals 0 implies x is equal to 1. So with this, we have gotten to limits for our objects that's revolved. It revolves around x is equal to 0 in terms of the coordinates. That's x equals to 0 and x is equal to 1. Okay, so now, which invariably means that if x is equal to 0, obviously here, let's say x equals to 1, let's say it's here. So it means the object looks like this. So this other part is not part of it. It revolves only on this half plane. You know, it's symmetrical. So now, what we have to do now is, let us, now draw, let's now, show the integral representation of this revolution. Let's show the integral representation of this revolution rather. Okay? Now we have this. So before then, what does the formula says? The formula says that when you have two functions, as we have gotten now, and we want to use the cylindrical, using the cylindrical method, or cylindrical shell method. Now we use this method that says that the volume of the revolution rather is equal to 2 pi integral running from a to b of the function. Because we are having two functions now, we have x is there, that is the distance of that particular object from the y-axis, then which is representing the radius. Okay, then f of x minus g of x dx. Okay, f of x minus g of x dx. Remember, this is the given equation. I mean, this is the standard cylindrical shell method when two curves are into play. So now, don't forget I said this x represents the radius, and this is the function. This is another continuous. They are both of them are continuous function. This a and b are the limits of integration, the lower limit and the upper limit. So we have what? 2 pi, then 0, 1, because we have x equals to 0 and 1. So 0, 1. 0 will come as the lower limit, while 1 will come as what? As the upper limit. So we have x into, when we subtracted our functions from the other one, we have what? X minus x squared. I think that's what we got there. Yes, x minus x squared dx. Okay, that is when we subtracted g of x from f of x. So from here now, we have what? So we have, let's expand this. So we have 2 pi integral of 1 and 0 of x squared minus x cubed dx. Okay, so with this, we have to integrate this and take the limits. So integrating that gives 2 pi. Let's integrate x squared, that is, you had 1 divided by 3, that's x is about 3 all over 3, minus you had 1 divided by 4, x is about 4 all over 4. Then we take the limits, 1 and 0, 1, 0. Okay, good. So now we can have our 2 pi multiplying this. That is when x is 1. So you use when x is equal to 1, you use when x is equal to 0. So when x is equal to 1, you have 1 cube all over 3 minus 1 raised to 4 all over 4. Then minus when x is now equals 0, 0 cube all over 3 minus 0, 4 all over 4. Obviously everything here will be 0. So you have this to be, let's write it here. B will now be 2 pi, okay, into 1 over 3. How we are getting that? Okay, minus 1 over 4. So our LCM will be 12. 3 here, what's 4? Then minus 4 into 12, 3, that's 1, 3. Then multiplying everything by 2 pi. Okay, so we have v is equals to 2 pi multiplied by 1 over 12, because 4 minus 3 is 1 over, it's 1 over everything over 12 there. So you have this to be 2 cancel this, you have what the volume now is equal to what, pi all over 6 cubic units. So that's the answer. So the answer is pi over 6 cubic units. So let's look at another example. I hope we understood this. Okay. Let's look at another example. Now, let's use another method there in this second example so that we'll be used to the two methods. So this time around, the example is this. Now we want to, in this example, we want to look at volume generated by rotating a curve. This time around now, we want to see when a curve is rotated, what volume will it produce to us. So example 2. Find the volume generated by rotating the curve y is equals to sine theta about x-axis. This time around is about x-axis for x is equal to 0 and x is equals to pi. Beautiful. So how do we solve this? Now this time around, let us use this method, because basically we want to see how the volume of a curve can be rotated about x or y axis. But this time around now, we want to consider it about x axis. So using this method that says the volume of revolution is what is equal to the pi of the integral running from a to b of the function itself all squared dx. Okay, now so in this case we have what the volume is equal to pi multiplied by, we have already been given the limit of integration to be 0 to pi. Beautiful. Now f of x, that's the function, which is y is equal to sine theta all squared, because that's just there, the x. So by the time we expand this, we have is equal to pi multiplied by, this will be what, sine theta, that's sine square theta, but remember, since the variable is in form of theta, so this one will not be dx again, it will be the theta. Okay, so the theta, you have 0 to pi, so now very invariably, you can open this up anyway. Invariably, we can change sine square theta into a standard version in such a way that it will be easier for us to, integrate. Because as it is now, it will give us a lot of problems. So, what is the trigonometric equivalent of sine theta? Let's recall sine square theta is the same thing as 1 minus cos 2 theta all over 2. So you can check that yourself. I hope you have learned about this trigonometry before. So you try that. Please find out. So sine square theta is what? 1 minus cos 2 theta all over 2. I hope you can still remember that. So check. Okay. So that implies that let's clean up everything here. So that implies now that what we want to do is what? We want to find v is equal to pi of 0 to pi of 1 minus cos 2 theta all over 2 d theta. Okay, so here we can bring this one here and have is equal to pi all over 2. Can bring this out because it's denominator. and it's a constant, pi 0 1 minus cos 2 theta d theta. So by the time we now integrate, we have pi all over 2. We now integrate this, it's when you integrate 1 with respect to the theta, you have what? You have theta minus, when you integrate cos 2 theta, remember when you integrate cos theta, you have what? You have sine theta. But now it is cos 2 theta because a factor 2 is multiplying theta here. So you have first of all divided by that 2. You have 1 all over 2. Now, when you now integrate cos theta, like I just said, it's going to be what? Sine theta. That is it. But because it is cos 2 theta, it will be what? Cos 2 sine 2 theta. If it were ordinarily cos theta, it will be sine theta. But now it is cos 2 theta. First of all, divide by this constant 2, 1 over 2. Then, since it is cos 2 theta, it will give you sine 2 theta. That is how it is done. Okay? Now, 0 is the lower limit and pi is the upper limit. There is no need of adding plus c because we are dealing with a definite integration. We have limits being given. We have lower and upper limits. So in this case now, that means we have to apply these limits. So we have is equals to pi all over 2. So when theta is equals to pi, we have pi minus 1 all over 2 sine 2 pi. Okay, the minus, the other one when theta is 0, 0 minus half sine 2 times 0. Okay, you close that. So we have pi all over 2 into pi minus half sine 2 pi is what? Sine, a pi is 180 radians, that's what? 2 pi will be what? 360 degree. Okay? 360 degree. I hope you are getting that. Okay? So minus everything here will be 0 automatically because this is 0. Sine 0, 2 times 0 is 0. 0 times half is 0. Everything here is 0. So you have what? And sine 360 degree. Times 360 sine 3. Recall sine 360 degree is equals to 0. Is equals to 0. So that implies that we have what? V now equals to pi all over 2 multiplied by pi minus everything here is 0 now because sine 360 is 0. 0. Okay? So that will be equals to pi squared all over 2 cubic what? Units. So that is it. So that is our V. That's our V. So the volume of that of the revolution of that curve is pi squared over 2 cubic units. So let's look at how we can show the real life application of the volume of revolution. How it is applied in real life. Let's quickly look at one example there. Now remember this wine, a wine cup, a glass cup of wine, or a wine glass is symmetrical. So in this concept, let's suppose we have this, our y and x axis. I want it to revolve probably around the y-axis or the x-axis. If we want to design, so let's say manufacturer is giving a specification, and along the line, that specification is given in terms of function. So if is to produce a wine glass, which is to be rotated along the x-axis, it will be like this, okay? It will be like this, something like this, something like this. I hope you understand. I'm trying to produce a wine glass now. Let's see this. Okay. It will, let's say something like this. But if it is the other way around, it will be like this, So that's just an illustration, okay? Now, let's really go to the business of the day in terms of that application. We want to look at the volume of revolution in the real life. Okay, now let's look at an example problem here. Or example. Look at the problem. A manufacturer wants to design a symmetrical wine glass. When we say something is symmetrical, you know that it can be divided into two equal half by having a half, what do you call it, half plane. Okay, it's symmetrical. That means you can probably divide it into two equal parts. So glass, by rotating a curve around, want to design a symmetrical wine glass by rotating a curve around the y-axis. This time around, we want to consider the y-axis. Okay, suppose the profile, suppose that is specification needed. Suppose the profile of the glass, is defined by the curve. And what is the curve? X is equal to square root of y. For the range of 0 less than equals to y less than equals to 9. Now this represents the size of the glass. Now to find the volume of the full glass, that is to rotate this, we rotate this particular curve around what we are given, around the y-axis. Okay, now like I was just trying to draw the other one. So the curve will be rotated along the y-axis. So let's use the Dix method. Let's use the Dix method that we just used now, which is a volume of revolution is with pi into the limit of a, b, are we getting that? Of f of x all squared dx. But in this case now, since we have to rotate along the y-axis, it should change to what? V is equal to pi ab f of y all squared dy. All right, beautiful. So that implies that v will be pi. The limit of integration is between 0 and 9, so 0 to 9. Then f of y, this function given to us, is what? Is root y all squared. Okay, dy. Yes, because our axis will be rotated along the y. We can't write x, even if you say x squared. What is x squared? X squared is standing as the root y, the y. The y will take place here because we are rotating along the y-axis. So we have to take differential coefficient of y. So now in this case we have pi integral of 0 to 9. This will be y dy, because the root of y squared is dy. Let's split it up. So what next? We're going to have, therefore, the volume of resolution will be pi into, okay, let's integrate directly. This will be what? Y squared all over 2. Yes. Then 0 and 9. All right. So we have what? Pi into, this is what? Our y is 9 here. That's 9 squared all over 2. Then we are done with 9. Then minus 0 squared all over 2. So that will be what? Pi multiplied by 81 all over 2. This is with 0. So which is going to be what? Which is going to be 81 pi all over 2 cubic units. So that is that about that. So with this we have come to the end of volume of revolution as one of the aspects of integrations application. So do well to click on the notification bell so that each time I upload a video you'll be duly notified, and always click the like button. I remain Dr. OJ. God bless you.